be here tonight, and there's nothing quite like two successive people telling you this is going to be a fantastic talk for this to not meet your expectations. So bear with me here. But what I want to do tonight is tell you about searching for cosmic gas with the largest telescopes. And so in a nutshell, I'm going to narrow down some really big topics. I'm going to narrow it down somewhat. And so the question I want to ask, if I can get this. Oh,
the other one.
Really?
You're going to need to click on it once. Just click on the screen.
See,
once.
I'm letting it down.
It's the technology. It's an entropy field.
That was looking awesome, right? Okay, so what I want to tell you about today is how we can understand galaxies. And so this is a Hubble Space Telescope image of a nearby galaxy. This is a little bit like the Milky Way. And so what you're looking at here are stars and the dust. So the dark regions is gas in the dark, dust in between the stars. And so I'm trying to understand objects that look like this. And the context in which I'd like to understand them is the model by which we understand the universe itself to evolve. And so the study of the universe itself is often called cosmology. And this is a piece of the universe that we predict to exist today if our eyes could see dark matter. So this is a dark matter image of a big piece of the local universe. And we think we understand this model pretty well. So we'd like to understand galaxies in this cosmological context. And we're going to do it using the biggest radio telescopes. And so this is a picture of the Square Kilometer Array. I'm part of a collaboration that's working to build this mega science project. And it will become the biggest radio telescope in the world very soon. And so I'm going to tell you a little bit about that towards the end. So to start off, the kind of galaxy that I'm going to tell you about today is called a spiral galaxy, or it's called a disk galaxy, and I might use those two terms interchangeably. And so what you're looking at here is a picture, it's an artist's rendition of our own Milky Way, which of course should be repeating and is not. There we go. And so what you're seeing is that artist's rendition changing an angle in the sky relative to our line of sight from the Earth, so from our vantage point. And you can see that the galaxies are going to look different on the sky depending on their orientation relative to us. And one of the reasons to study spiral galaxies is because we live in one. So if you've ever been fortunate enough to see the Milky Way in the night sky, so here's a rendition of that. What you're looking at is the disk of the Milky Way from our vantage point within the Milky Way. So imagine putting yourself inside a dinner plate and looking along the line where the rest of the plate is. And so there are lots of reasons why it makes sense to focus on spiral galaxies for the kind of research that I'm going to tell you about tonight. But one of them is that they tend to have gas among the other types of galaxies. So if we're going to look for cosmic gas, it's helpful to look at a type of galaxy which we expect might have gas in the first place. So let's go back to this picture from the Hubble Space Telescope of a nearby galaxy. And to give you a sense of scale, this white arrow here is about 100,000 light years across. So we're on a scale vastly, vastly larger than the Earth or the solar system. To give you a sense of scale, a galaxy like the Milky Way has about 100 billion stars in it. And I'll come back to that right at the end. So when you look at a picture like this from, say, the Hubble Space Telescope, the mental image which you should have in mind is something that looks like this. So this is a simulation of the gas and the stars swirling around the center of the galaxy. So galaxies are actually really dynamic things. It's just it takes so long for the gas and the stars to get around the galaxy that they appear static in our night sky. Does anybody want to hazard a guess as to how many times the Earth has gone around the center of our galaxy since the dinosaurs went extinct?
None.
Exactly. How long ago did the dinosaurs go extinct?
65 million.
Something like that, 65 million years ago. And we've gone about a quarter of the way around our galaxy since the dinosaurs went extinct. Yeah?
Isn't it 220 million years for us to make the full cycle around?
Yeah, that's close to a quarter. 220, 65, did I do that? Yeah, I did that right. You are finding that it turns out physicists actually can't do math on the spot. So if you want to split a check after dinner, don't ask the physicists. They'll get it right to an order of magnitude, but that's what it is. Okay. So the thing that's making the gas and the stars orbit around the center of the galaxy, right? The reason why they're moving in a circle is because they're being pulled that way. And in order to pull something, right, to deviate it from a straight line, you need a force. And the force that's at work here is gravity. So it's the gravity of the gas and the stars and everything else that's in the galaxy that's forcing those stars and gas in a circle. And if you think about it, the stronger the force is going to be, the more gravity you have, the more of a force you're going to impart, and the faster things are going to go, right? And so if we could measure how fast the gas and the stars move in a galaxy, we'd actually have a measure of the pull of gravity. And luckily for us, we actually understand how gravity works pretty well, so we can work out how heavy the objects are in a galaxy based on the motions and tying that through the gravitational force. And so the take-home message here is that galaxies are ruled by gravity. Almost everything that you see in the sky, those structures that we see in galaxies, up to 0th order, are dictated by the force of gravity. So we can actually use that as a tool, and we can look at stars and gas and galaxies and measure how fast they're orbiting around the galaxy center, and then connect that to galaxy masses based on Newton's laws. And so when we do that, we often get a curve that sort of looks like this. So there's orbital speed on the y-axis here. So this is how fast the gas and the stars are moving. And then we can do that as a function of distance from the galaxy center. So that's what's on the x-axis here. That's what this r stands for radius, and it's measured in light years, basically. And the points here show what we measure for a nearby galaxy. If you've ever heard of the triangulum galaxy, that's what this galaxy is here. And you can see that the points sort of trace this curve that rises in the center and then becomes more or less flat. This one's actually continually rising. But you can see that the gas is moving really fast, quite far away from the galaxy center, right? The galaxy's all over here, but when we measure gas that's over here, we can still see that it's actually going quite quickly. And if you think about that, it's a little counterintuitive, right? So further and further away from this galaxy, these points that the gas isn't going any slower. And so that was a hint about 50 years ago now that there's actually more to galaxies than meets the eye. So if all that was doing the forcing in this galaxy were the gas and the stars, you'd expect to see a rotation curve that looks like this. And in fact, what we measure is this. And the difference between what we expect from what we can see and what we measure is attributed to something that we can't see called dark matter. So if we go back to this picture of a galaxy, the second mental picture that you should keep in mind is something that looks like this. There's much, much more than meets the eye in a galaxy. And the parts of the galaxy that we can see, the gas and the stars, are deeply embedded within this much, much bigger dark matter halo that we think has most of the mass in the galaxy. So galaxies are ruled by gravity, and gravity is ruled by dark matter. Now, I wish I could tell you what the dark matter was. If I could tell you what the dark matter was, I would not be here. I would be booking my flight to Stockholm. Because lots and lots of people want to know what the dark matter is, right? And so if you sort of think about this and step back and sort of think a bit, and if you're a glass half empty kind of person, you might be saying to yourself, well, game over, right? We just said that most of the mass in a galaxy is made up of dark matter. We don't know what the dark matter is, right? So maybe we should just go home, right? But it actually turns out that even though we don't know what the dark matter is, we can observe astronomical objects precisely enough to infer its physical properties. And the crazy thing about physics is that if you can understand the physical properties of something, you can actually model its behavior, how it's going to affect galaxy formation, without actually knowing what the dark matter is. And so that's how we're going to make progress. We're going to move forward by using the physical properties of the dark matter, even though we can't identify the particle or whatever it is that's causing the dark matter to be there in the first place. And so this picture of the dark matter universe was created on a supercomputer using exactly that philosophy. So we can embed a very early universe with particles that represent the dark matter, and we follow the physics that we think that dark matter obeys, even though we don't know what the dark matter particle is, and we see what the universe produces under the influence of that physics. And it turns out that our universe is pretty well explained by a dark matter particle that does only one thing. It responds to the force of gravity. And again, gravity is something that we understand pretty well on these